Hi everyone. Today we are going to discuss about motion of charges in electric and magnetic field. In electrostatics, we have seen a charge in electric field will experience a force F equal to Q into E. Similarly, a charge Q moving in a magnetic field with a velocity V will also experience a force. The force experienced by a charge moving in magnetic field is called Lorentz magnetic force, and the force is given by F equal to Q into V cross B, where V is the velocity and B is the strength of the magnetic field. The scalar expression for the force is given by F equal to Q into VB sin theta, where theta is the angle between velocity and magnetic field. The direction of the force is perpendicular to both velocity and magnetic field. Now we will discuss some special cases. First one, if the charge is at rest, then V is equal to 0 and consequently Fm will be 0. So now a stationary charge in a magnetic field does not experience any force. If theta is 0 degree or 180 degree, the charge moves parallel or anti-parallel to the direction of magnetic field, then also we can see that sin theta will be 0, therefore force will be 0. Third case, if theta is 90 degree, sin theta become 1 and force Fm will be equal to QVB, and this will be the maximum force experienced by the charge moving in a magnetic field. Force acting on a moving charge in a uniform electric and magnetic fields. Consider a charge Q moving with velocity V in a region in which both electric and field E and magnetic field V exist. Then it experiences both electric and magnetic forces. The electric force is given by Fe equal to Q into E, and the magnetic force is given by Fm equal to Q into V cross B. Therefore, the net force acting on the charge is given by the sum of both electric and magnetic force. Therefore, F equal to QE plus Q into V cross B. Here, Q being a common term can be taken outside, and we get F equal to Q into E plus V cross V. This force is called Lorentz force. Lorentz force is the total force acting on a charge moving in a combined electric and magnetic field. Force on a current carrying conductor in a uniform magnetic field. Consider a conductor of length L, area of cross-section A, placed in a uniform magnetic field B. Let theta be the angle between the direction of current and the magnetic field. Then the force experienced by each electron is given by F equal to Q into V cross B. Let n be the number of mobile charges per unit volume. It is also called mobile charge density, and V be the drift velocity of charges. Then the total number of mobile charges will be given by N into L into A. Therefore, the net force acting on the charges is given by NAL into Q into VD cross B. This can be rearranged and we can write as F equal to NA VD into Q vector L cross vector B. The current I is given by NAVD into Q, which is the relation between current and drift velocity. So substituting for NAVDQ as I, we get the force on the conductor as F equal to I into L cross B. This can be written in scalar form F equal to DIL sin theta. The direction of force on a current carrying conductor in uniform magnetic field is given by Fleming's left-hand rule. Fleming's left-hand rule. Hold the middle finger, forefinger and thumb of left hand in mutually perpendicular direction, such that the middle finger shows the direction of current, forefinger shows the direction of magnetic field. Then the thumb will show the direction of force on the current carrying conductor. Motion of a charge in magnetic field. Here there are two cases. Motion of a charge in magnetic field. When the velocity of the charge is perpendicular to magnetic field. When the velocity of the charge is perpendicular to the magnetic field. The region where the magnetic field is acting perpendicular to the plane. The region where the magnetic field is acting perpendicular to the plane. Assuming the image and inwards charge particle is entering this field. Assuming that perpendicular to the magnetic charge particle is entering this field. Charge Q perpendicular to the magnetic field. Perpendicular the charge Q magnetic is having its velocity then perpendicular to the experienced magnetic force. Then the magnetic force acting on the charge is a magnetic force QVB. The magnetic force acting on the charge is given theta is the angle between velocity V and the magnetic field. Theta is the angle between 90 degree velocity V and the magnetic field. So the equation 90 degree becomes Fm 90 becomes QVB. So the equation, the direction of force Fm equal to QVB given by the direction of force Fleming's left hand is rule. Given by applying Fleming's left and Fleming's left hand the force. By applying the Fleming's left hand rule, we see that the force downwards as shown in the figure will be due to this force downwards as shown in the figure moves due to this along a circular path. Charge moves along a circular path. It experiences a centripetal force. When a charge given along a circular path equal to it experiences a centripetal force. M is given mass of the charge equal to R. M is the radius by R of the orbit. M is the mass of the charge and R is the radius. The centripetal force in this case is provided by the magnetic force. The centripetal force in this center is provided by the magnetic force acting towards the center of this orbit. Substituting for FC and F equal to we get mv square by R equal to substituting for FC and Fm we get mv square by R equal to Q. Solving for R, we get R equal to mv by qb. Solving for R, we get expression for the radius of the orbit. This gives the expression for the time period of the orbit. Time period is the time taken by the charge to complete the time circular motion. Time period is the time taken by the charge to complete one circular motion. The velocity time period is given where 2 pi r is the circumference by circular the velocity v. Substituting for 2 pi r is the circumference of the circular we get t equal to 2 pi by v for r, and v from the previous equation we get t equal to 2 pi by v 2 pi m by qb. We get t equal to the frequency by qb. The number of circular motion made by the charge in the 1 number second. Circular motion made by the is equal to in 1 by 1 second. Then frequency nu is equal to 1 by frequency where t is the time period. qb by 2 pi m. So frequency nu is equal to the angular frequency 2 pi omega is given by 2 pi into nu. The angular frequency for nu omega is given by omega 2 pi into v by substituting for nu. We get this frequency equal to is also known as by cyclotron frequency. This frequency is also known as cyclotron frequency. Motion of a charge in magnetic field. Second case, when the velocity of the charge makes an angle with the magnetic field. Here we have the magnetic field along the x-axis and the particle entering the magnetic field with velocity v making an angle theta with respect to the direction of magnetic field. Then this velocity can be resolved into two components, one along the x-axis called v parallel and another along the y-axis called v perpendicular. The v perpendicular is component by v sin theta and v parallel is given by v cos theta. Since v perpendicular is perpendicular to the magnetic field, the charged particle will execute a circular motion in a plane perpendicular to the magnetic field. So the centripetal force mv perpendicular square by r is equal to q into v perpendicular into v, because when the charge executes a circular motion, the centripetal force is provided by the magnetic force acting on the charge, and that is given by qvb. On simplifying, we get r equal to mv perpendicular by qb, or r equal to mv sin theta by qb. The time period is given by 2 pi r by v perpendicular, and substituting for v perpendicular we get t is equal to 2 pi m by qb. So this is the time period of the particle as it executes circular motion in the magnetic field. But here the particle is also having a velocity component parallel to the magnetic field. Due to this v parallel, the particle will move along the x-axis along with the circular motion which it executes. As a result, the path of the particle will be a helical path, or it is called a helix. The pitch of a helix is the distance between the adjacent turns of a helix. The pitch is the distance moved along the magnetic field in one time period. Therefore, the pitch can be written as t into the velocity along the direction of the magnetic field, that is V parallel. P equal to t into V parallel. So here we substitute for t and we get P equal to 2 pi m V parallel by QB. Again we substitute for V parallel as V cos theta. Then we get the expression for pitch P equal to 2 pi m V cos theta by QB. Cyclotron. Cyclotron is a machine to accelerate charged particles or ions to high energies. Here the diagram of a cyclotron is given. The principle: a charged particle made to repeatedly move along a circular path of increasing radius in a crossed electric and magnetic field attains high energy. In the construction part of this cyclotron, we see that there are two D-shaped hollow cylinders called Ds. The Ds are connected to high frequency oscillator. The Ds are placed in a magnetic field. Here the magnetic field is perpendicular to the image and outwards. The particle to be accelerated is placed at the center of the D. The whole arrangement is placed in a container with vacuum in it. The working of cyclotron. Initially, let us assume that one of the D is positive and the other is negative. Then, if the charged particle is positive, then it will get attracted to the negatively charged D. As it enters the D, its velocity is perpendicular to the magnetic field and hence it executes a circular motion inside the D. By the time the particle comes out of the D, the polarities of the D's will change. Then the other D will become negative and the first D will be positive. So the charge gets accelerated towards the second D. It enters the second D with a higher velocity, hence it executes a circular motion with larger radius. Again, when it comes out of that particular D, the polarity of the D's changes and the particle will get accelerated towards the other D. With a higher velocity, it enters the other D and hence it executes a circular motion with even larger radius. So this process is repeated, and after each rotation the radius goes on increasing, and finally the particle, when it is moving along the circumference of the D, it will have maximum energy and then it will be deflected and taken out. The theory part. The magnetic force experienced by the charge is given by QVB sin theta. Here the velocity of the particle is perpendicular to the magnetic field, hence theta becomes 90 degree. So this magnetic field provides the required centripetal force for the particle to execute circular motion. If the particle is having mass m and it is moving with velocity v and the radius of the path, circular path is r, then the centripetal force is mv square by r, that is equal to the magnetic force qvb sine 90. So simplifying, we get r equal to mv by qb. Here r is the radius of the circular orbit. If t is the time period of the high frequency oscillator, then at resonance t is equal to 2 pi r by v. The time period is the time taken by the particle to execute one circular motion, and that will be equal to the circumference of the circular orbit divided by the velocity of the particle. So here we substitute for r from this first equation, and then we get t is equal to 2 pi m by qb. The frequency of circular motion is given by nu equal to 1 by t, nu equal to qb by 2 pi m. Here we see that charge is a constant, b is a constant, mass of the particle is a constant. That means the frequency is independent of the radius of the orbit. The expression for maximum energy of a particle in cyclotron. We know the kinetic energy of a particle is given by half mv square. Here the velocity is given by qbr by m. So therefore the kinetic energy can be written as half m qbr by m whole square. The expression for velocity is obtained from the previous equation for r. So kinetic energy equal to, simplifying, we get it q square b square r square by 2m. Now the kinetic energy is maximum when the charged particle is moving along the circumference of the Ds. In that case, r become capital R, which is the radius of the D. Therefore, the maximum kinetic energy Ke max equal to q square b square capital R square by 2m.